Hello everyone. In this video we'll just work a standard predicate derivation. It's kind of an interesting one. Please grab a piece of paper and a pencil so that you can practice along. This is the proof we're going to work. The two primary assumptions start with an existential generalization. There's an x, tilde bxm, and for all y, if cy, then not gxy. The second primary assumption is for all z, tilde for all y, if wy, then gzy, then bzm. And the statement that we're going to derive is the universal generalization for all x, if cx, then not wx. Once you have that all down, go ahead and pause the video and see if you can come up with an idea for how to structure this proof. And when you're ready, resume the video. Okay, so one very natural, you may have come up with this idea, one very natural way of thinking about this derivation would be to try to prove an instance of this universal generalization. For instance, if CA, then not WA, and then to use universal introduction on that statement to get to the conclusion. A universal introduction would work on this statement since the name A never appears in any of the primary assumptions. By the way, there is a name in the primary assumptions, but the name is M. Okay, and so then maybe you could think that, well, that's a conditional, so you should use conditional introduction. And you might come up with the idea of inserting a subderivation. Something like this, where you start with CA and then you land on not WA. Okay, that's a perfectly reasonable strategy, but that's not the strategy we're going to follow in this proof. Okay, so I'm going to go ahead and erase this, and if you started out this way, go ahead and hang on to that. You might be able to work it out. I'm sure you can actually. But there's another way that we're going to do this that I think is going to be more instructive and maybe even more fun. So the way I thought of doing this is simply by using existential elimination. So we're going to start an assumption for existential elimination on the existential generalization in line 1. So I'm going to drop the quantifier, and in this case, the outer parentheses are going to go with it. I'm going to replace these two occurrences of x here and here with the name A, which is to remain isolated to our subderivation. Okay, so tilde BAM ampersand for all y, if CY, then not GA. Y. That's an assumption for existential elimination. And then the goal in that subderivation is going to be to get to our target sentence for all x, if cx, then tilde wx. Okay, so then that would give us our target sentence along the main scope line as an application of existential elimination on lines 1 and 3 through something. We'll figure it out later. Okay. Once again, we could think about getting this conditional by establishing an instance, this universal generalization from a conditional that we get by conditional introduction, but we won't worry about doing it that way. We're going to get an instance here. CB horseshoe tilde WB but we're not going to get it by conditional introduction. So we are going to aim for this conditional. If we get it, then we can use universal introduction on it. Why did I put the names B here? Why didn't I use the name A or M? Those names already exist in our proof. So why introduce the name B? If you don't know the answer, go ahead and hit pause and look over our proof so far and revisit the inference rule universal introduction and see if you can figure out the answer. So I'm putting the name B in here. I have to have a name in these two positions to apply universal introduction. B has the advantage of not appearing in any live assumptions. So we have 3 live assumptions here at this point in the proof. And we have names in those assumptions, the names A and M, right? So if I get a conditional with those names in it, I cannot apply universal introduction to it. So I'm going to, in trying to get this universal generalization inside this subderivation, I'm going to have to get an instance that's totally neutral. It has a name that does not appear in any of the live assumptions. That's one of the restrictions on universal introduction. So I'm just planning ahead, and I'm gonna try to get a sentence that this rule actually will apply to. Okay. So at this point, why don't you hit pause and look at the sentences we've got to work with. Really, we're already working with line 1 because we're working with its neutral instance on line 3. And then we have line 2, the universal generalization, which is, at least up to a point, pretty easy to work with. So why don't you look at lines 2 and 3 and maybe try to hammer out a few steps that are going to get us, get this subderivation moving. And one other little clue here is that we're going to try to prove this conditional, but we're not going to do it with conditional introduction. So there's a little puzzle for you. How are we going to prove a conditional if we're not going to use conditional introduction? Go ahead and hit pause. Let's see how far you can get, and then resume the video. So one thing that we can do right away is just take line 3, it's a conjunction, so we can just break it into its component sentences by conjunction elimination. So we've got tilde B, A, M, and we've got the universal generalization for all y. If cy, I got ahead of myself. If cy, then tilde G, A, Y. Those both come from line 3, ampersand elimination. Okay. Might also look at line 2. Okay, so I want to work with an instance of this generalization. That means I should use universal elimination on line 2. And that means I have to drop the quantifier, and in this case, the outer parentheses that go with it. And I want to instantiate a particular name in the position of Z. What name should I use? Tilde for all y. If wy, then g a y, then b a m. I've instantiated the generalization on line 2 to the name a. The variable of quantification is z, so when I saw those z's, I replaced them with a's. But why? There's a couple of reasons. One is that having A in the first position after the two-place predicate B gives me and actually having an M in the second position after the two-place predicate B gives me something that looks very similar to line 4. Line 4 is the denial of the same statement. The consequent of the conditional on line 6 is BAM, and line 4 is the negation of BAM. So by instantiating this variable to A, I'm making contact with another line of my proof, and that's going to give me an opportunity to apply more inference rules. You might be looking at this and thinking modus tollens. Yeah, that's a good idea. The other advantage is that we're making connections here. Line 5 has the two-place predicate G with the name A after it, and I've got an A on line 6 in the same position following the two-place predicate G. That means there's going to be some contact here that we can exploit later on to help this proof along. Okay, so the next step would be to go ahead and apply modus tollens. Okay, so I have a conditional on line 6. The main connective is that horseshoe right there in the middle. And I have the denial or the negation of the consequent of the conditional. So if you look at modus tollens, that is exactly the input for modus tollens. The output for modus tollens is the denial of the antecedent. Okay, so here's my antecedent. It starts with the tilde and ends at the closed paren. And so if I'm going to form the denial of the antecedent, I have to put another tilde in front of it. So this comes from 4 and 6 modus tollens. I'm going to go ahead and drop both of those negation signs. For all y, if wy, then gay. That's line 7, double negation. Okay. So now let's draw our eyes to lines 5 and 8. 5 and 8. We're going to be getting pretty far by using lines 5 and 8 on our way to this conditional here. All right? So what I want you to do is go ahead and hit pause and see how close you can get to this conditional just by paying attention to lines 5 and 8. All of the other lines of our proof, they can just fade into the background for now. So don't look at lines 1, 2, 3, 4, 6, or 7 anymore. Focus in on 5 and 8 and see how close you can get to this conditional. Go ahead and hit pause and resume when you're ready. Okay, so what we want to do with lines 5 and 8, they're both universal generalizations, and we want to instantiate them. We can instantiate universals to any name we want. We could instantiate them to A, we could instantiate them to M, or any other name. We should not instantiate them to A or M, however, because we're going to end up with conditionals that have those names in them. And when we play around with those conditionals, as we'll do here in a moment, we will get a result that we cannot apply universal introduction to. Okay, A and M are going to be a problem if our plan is to apply universal introduction. Because universal introduction will not apply to names that appear in live assumptions, and those two names do. So we have to choose a different name. I've already anticipated this, and so we should instantiate both of these to B. Let's work on line 5 first. C, B, horseshoe, tilde, G, A, B. That's line 5, universal elimination. And then on line 8, W, B, horseshoe, G, A, B. That's line 8, universal elimination. Okay. Let's take a look at line, let's figure out something we could do for line 11. Okay. We're trying to get if CB, then tilde WB. And we should be paying attention to lines 9 and 10. Do you see a way of making that work? Here's one thing that will help. Let's do transposition on line 10. Transposition says you can take it's sometimes called contraposition. You can take the two sides of a conditional, trade them places, okay, but then add tildes to both of them. So the result would be tilde, GAB, horseshoe, tilde, WB. That's line 10, transposition. Now let's look at lines 9 and 11. 9 and 11. If CB, then not GAB, and if not GAB, then not WB. If we take 9 and 11 together, that actually gives us the sentence we want. 9 and 11, thanks to hypothetical syllogism. That's one of our SD plus rules of inference. Very useful in this proof. Because of that rule, we didn't need to do conditional introduction. Okay, at this point we're home free. The next line is line 13, and that's simply an application of universal introduction on line 12. So once we have that statement, we can move it to the next outer scope line. The name A, remember, is restricted to this subderivation. It doesn't appear above the subderivation, and it's not allowed to appear below it. So once we have this universal generalization, we can move it to the next outer scope line thanks to the rule existential elimination. The existential generalization that is needed as input for this rule is up on line 1, and then the subderivation runs from 3 to 13. Okay? So there's another little predicate derivation for us.